The only examples of intelligent systems in the world that we have are the natural examples. Ourselves, the other animals, and some types of plants are biological robots from which we can try to get inspiration. In contrast to our artificial robots, biological robots are incredibly robust, adaptable, and efficient. For this reason, many researchers have studied the so-called bio-inspired or biomimetic solutions. There are two typical features of bio-inspired solutions. One is the simultaneous harmonious design of hardware and behavior, rather than first designing the robot and then have the software force a particular behavior. Another feature is the simplicity of control, often by employing a relatively direct connection from sensing to actuation, rather than having complex internal representations. The simplest example of a complex behavior with very simple sensing and actuation is bacterial hemotaxis. Hemotaxis is the directed motion of an organism towards environmental conditions it deems attractive or away from surroundings that it finds repellent. A bacterium like E. coli has one type of actuator, rotating flagella. When the flagella rotate in one direction, they propel the bacterium forward. When they rotate in the other direction, they produce a chaotic tumbling motion. The movement of E. coli is a sequence of smooth runs punctuated by intermittent tumbles. The tumbles are activated more frequently when the nutrition gradient decreases. Therefore, the bacterium will spend more time in areas with more nutrition. The bacterium implements a search strategy without making a map of the environment or planning a path, but just by implementing a simple link from sensing to actuation. Sometimes the simplest solution is the best. For example, the first robot vacuum cleaners used the strategy of bouncing around walls randomly to explore the environment. It's not the most efficient way to do it, but you can implement it using only bump sensors. Today, we'll look at Breitenberg vehicles. These are hypothetical machines imagined by Valentino Breitenberg in the influential book called Vehicles. These simple machines will show how complex behavior can arise from simple sensorimotor connections. We will build these imaginary vehicles out of motors and sensors. You can imagine them as bacteria floating in the ocean searching for food, or like robots moving in a plane, similarly to a duckybot. This is Vehicle 1. There are one motor and one sensor. The link from the sensor to the motor shows that increasing the quantity perceived by the sensor increases the motor speed. Because there is only one motor, the vehicle cannot steer. Its motion will be a gentle tumble due to perturbation. Let's say that this is a light sensor. This vehicle goes faster when near light. It will speed up, but then it will pass the light. It will slow down and come to rest forever in dark areas. Vehicle 2 has two motors and two sensors. You can see it looks like a duckybot. It is a differential drive with a light sensor on the front. It's the other way around. The duckybot was designed to be similar to vehicles like this. We have three wiring variations, A, B, and C, depending on how you connect the sensors to the motors. We can choose different weights for the connections for each type. We can have the connections excitatory, which means that more light gives faster motion, or inhibitory, which means that more light gives slower motion. Breitenberg called Vehicle 2A fear, because it escapes from light sources. Imagine what happens when there is a light source to the right. Because the right motor is more excited, it will go faster, and the vehicle will turn away from the source. An observer would say that the vehicle experiences fear. Vehicle 2B is called aggression. Here, the wiring is inverted. So if there's a light source, the vehicle will turn towards it. The vehicle will point eventually straight at the light, increasing the speed until it hits it. In both cases, the connection is excitatory, but the wiring changes the behavior. Vehicles 3A and 3B are called Lover and Explorer. Again, we have direct and crossed wires, but with a minus sign. You can imagine that 3A will orient itself towards the light. However, the closer it gets, the slower it will go, eventually positioning itself so that it will stare at the light, permanently admiring it like a lover. 3B will go towards the light, but will come to rest away from it. It could then spot another light and explore a different part of the world. We can make the vehicles more complicated by adding more sensors. We can have a sensor for light, one for chemical concentration, one for oxygen, and so on. And you can have a vehicle search for nutrients, move away from possible dangers, all without an explicit representation of goals and values. Another way to make the behavior more complex is to shape the activation function from light intensity to motor velocity in a nonlinear way, or introduce some dynamics in the response. In the rest of the course, we will study sophisticated algorithms to implement perception and decision-making. However, always keep in mind Breitenberg vehicles. Complex behavior can arise by relatively simple interconnections of sensing that question. A quote from engineer Antoine de Saint-Exupéry says that perception is achieved not when there is nothing left to add, but when there is nothing left to remove. And remember that software that doesn't exist doesn't contain any bugs. In this video, we have looked at how complex behavior arises from simple sensorimotor interconnections in bacteria and Breitenberg vehicles. The lesson to be learned is that we need to look for the most straightforward solution to a problem. Only if the simple solution doesn't work should we increase the solution's complexity.